In the previous sections, we analyzed uniform circular motion and the concept of centripetal acceleration. Newton's second law indicates that whenever an object accelerates, there must be a net force to create the acceleration. Thus, for an object undergoing uniform circular motion, there must be a net force that provides the centripetal acceleration. This force is called the centripetal force, or F sub c, and the second law tells us it must be equal to the object's mass times the centripetal acceleration. This force must point in the same direction as the centripetal acceleration, that is, toward the center of the circular motion. Let's explicitly define the centripetal force. The centripetal force is the name given to the net force required to keep an object of mass m moving at a speed v on a circular path of radius r, and it has a magnitude that equals mv squared over r. The direction of the centripetal force always points in toward the center of the circle and continually changes direction as the object moves. Here it is important to note that the centripetal force is not a new and separate force created by nature, but rather it is the vector sum of the radial forces acting on an object undergoing circular motion. Therefore, the centripetal force should never appear as a labeled force in your free body diagrams. It will be a single force or combination of forces we have already considered, such as weight, tension, normal forces, or friction. In certain situations, it may be easy to identify the centripetal force, and in others it may be more complicated. However, the approach to solving circular motion problems falls naturally within our existing problem-solving strategy. First, draw a figure if one is not provided for you. Second, identify the object or objects in the system. Third, draw the free body diagram for each object. 4. Choose a convenient and appropriate set of coordinate axes. 5. Resolve the vectors in the free body diagram down into their x and y components. 6. If the object is undergoing circular motion, identify the centripetal force from the free body diagram and set it equal to mv squared over r. Let's look at a couple of examples of circular motion and how we identify the centripetal force in each situation. Consider the example of a ball tied to a string of length L that is swinging around a circle where the string makes an angle theta with the vertical. We begin by drawing the free body diagram for the forces acting on the ball. We have the weight straight down and the tension, which is directed along the string. Next, we choose a coordinate system. Let's set positive y straight upward and positive x right to left so that it points in toward the center of the circular motion. Now we resolve the forces in the free body diagram down into their x and y components. The weight already lies along the negative y direction, so the only force we have to break down is the tension. It has an x component that points along the positive x direction and a y component that points in the positive y direction. We have circular motion, and with the vectors in the free body diagram now resolved, we should be able to identify what the centripetal force is. Notice that a force labeled F sub c does not appear in the free body diagram. Rather, F sub c will be equal to the sum of the radial forces, which are the forces that either point straight in or straight away from the center of the circular motion. Looking at the free body diagram, we see that we only have one radial force, T sub x, and it points in toward the center of the circular motion. Therefore, F sub c is equal to T sub x, and we can always set F sub c equal to mv squared over r. T sub x can be written in terms of the tension and the angle theta, and the radius of the circle r can be found from theta and L, the length of the string. Let's consider another example of centripetal forces. Here, a car travels around a flat curved part of a roadway. Let's draw the free body diagram for the forces acting on the car. In the vertical direction, we have the weight of the car, which points straight downward, and the normal force due to the roadway, pushing straight up on the car. We know we have circular motion, but neither of these forces can provide the necessary centripetal force to turn the car in a circle, since they don't point along the radial direction. Therefore, there must be another force that provides the centripetal force. Here, it is static friction between the tires and the road. Notice that it points in toward the center of the circular motion. The friction is static since the car's tires are not sliding along the radial direction. You may know from experience that if you try to turn a car on an icy surface with no friction, it just continues to move in a straight line in accordance with Newton's first law. From the free body diagram, we identify the centripetal force as being equal to the static friction. The larger the static friction force, the greater the speed the car can safely take the curve. However, the maximum static friction force is equal to mu sub s times the normal force. We can use this fact to find the maximum speed the car can safely take the curve. Setting the maximum static friction force equal to the centripetal force, which equals mv squared over r, and solving for v, we find v is equal to the square root of r times mu sub s times the normal force divided by the car's mass. Since the car is on a flat roadway and not accelerating in the vertical direction, the normal force on the car must be equal to its weight, mg. We can make this substitution into our expression for the speed. We see that the mass of the car cancels, and we find that the maximum speed one can take the curve to be equal to the square root of r times mu sub s times g. As long as you take the curve at a speed less than v, the static friction force will be able to provide the necessary centripetal force to keep your car moving on the circle. The fact that the result is independent of the car's mass tells you the maximum safe speed to take the curve applies to all vehicles, including small cars and big trucks. A passenger riding in the car must also experience a centripetal force that keeps her moving on the circular path. If the speed is not too great, this force is provided by static friction between her and the seat upholstery. However, at higher speeds, this force will be insufficient, and she will slide to the outside until the normal force from the inside of the door provides the centripetal force to move her in a circle. Passengers have the feeling of being thrown to the outside and pressed against the door. They might even say there is a force pushing them to the outside and up against the inside of the door. However, since they are moving along a circular path, they are accelerating, and therefore they are in a non-inertial reference frame. A person at rest on the ground watching the car drive around the curve would be in an inertial reference frame where Newton's laws are valid. They would correctly identify the forces acting on the passenger, specifically that the normal force from the inside of the car door is responsible for the centripetal force. Another way to think about this is the following. The passenger in the car wants to obey Newton's first law and continue to move at constant speed in a straight line. However, as the car turns, the inside of the door gets in her way and forces her to move in a circle instead of along a straight line path. To summarize this section, the centripetal force is the vector sum of the radial forces acting on an object undergoing circular motion. The magnitude of the centripetal force is equal to mass times the centripetal acceleration, or mv squared over r. The direction of the centripetal force changes continuously and always points in toward the center of the circular motion.